Alrighty, so this was asked for in terms of figuring out chi squared and how it related to Hardy-Weinberg and vice versa. So I have two questions, and I'm going to walk through each of them. These are totally new and linked in this email. So the first one, in a population of Venus flytraps in North Carolina, you observe 150 that can eat large flies and 400 that can eat only small flies. If the ability to eat large flies is small s recessive, what is the allele frequency? So again, we have to figure out what I'm looking at and what I'm trying to find. So here's what I know. I know 150 can eat large flies, 400 that can only eat small flies. I know that large flies, 150 divided by 550 equals my Q squared value. I know that because that is the recessive, and the phenotype and genotype are going to be the same. Keep in mind that the 400 thus represent P squared and 2PQ together, both dominant. So you cannot just take the square root of 400 divided by 550 to find P. You have to start with Q. So I take the square root of Q, which so Q squared is going to equal 0.27, and what that means is that is the frequency of recessive individuals within the population. So the frequency of recessive individuals, it's still a frequency. Moving on from there, in order to find Q, I take the square root. So Q equals the square root of 0.27, which is 0.52. I can then put that number, which is Q, into my equation where I say P plus Q equals 1. So P then equals 0.48. So now I have the two numbers that are actually going to do me the most good. Okay, so I have the frequency of recessive alleles, 0.52, and the frequency of dominant alleles, 0.48. That's within the entire population. All alleles are accounted for. Moving on to the second question. A store sells Venus flytraps and they have 56. That's a terrible question. Whatever. A store sells Venus flytraps. They have 56 plants in the store. How many would you expect to eat large flies? So here's what you have to say. Well, which are my individuals who can eat large flies? The individuals who can eat large flies are my Q squared. Okay, so my Q squared value is what I'm looking for. What is the frequency above of Q squared individuals? 0.27. What is the number of plants at the store? 56. So what I do is I take the total number of plants in the store, 56, and I multiply it by the frequency in which I would expect to see homozygous recessive plants. I put those together, I get 15 plants. Rounding again, you can't have a part of an individual, so you have to round. So 15 plants eating large flies is what I would expect to see in the store. I come down here and I see, what do I actually see? Well, I see that there are 25 plants in the store that can eat large flies. This is my observed value. Up here, this is my expected value. So out of that 56, I have two options. I'm doing this based on the phenotype. You eat large flies or you don't eat large flies. So my first option is phenotype A, where we eat large flies. If I can spell eat. Eat large flies. This would also be considered, if you're keeping track, my Q squared. Over here, my second option is eat small flies. And again, I'm just comparing the phenotype, so I only have two degrees of two individual options. So this would be considered P squared plus 2PQ. Again, two phenotypes, but altogether I have to account for all three different genotypes. So if we come down here, what is my expected value of individuals who eat large flies? 15. What is my observed? 25. Over here, what is my expected that would eat small flies? Expected would be 41. How did I get that number? I said, well, if 25 of 56 are eating large flies, then the remaining 41 must be eating small flies. My observed is that of 31. Did I misspeak? I misspoke. Okay, excuse me. Let me refresh. So eating small flies, how do I get my expected? My expected is being compared to the 15 right here. So if 15 are expected to eat the large flies, then 56 minus 15 is 41, and that's how many I would expect to eat small flies. Whereas what I observed is I take the 25 that eat large flies that I observed, and I subtract that from the 56 that are totally in the store. So everything should equate mathematically. So now I'm going to do my chi-squared analysis. So I take my observed minus my expected, square it over the expected. Add that to the other side. I do the math, and that's going to give me 9.11. I have two options, option A and option B, which means I have 1 degree of freedom, and my critical value for 1 degree of freedom is going to be, if I take a look here, let's put this over here on the side, my degree of freedom is, I just blurred that out, my degree of freedom is 3.84. So my critical value for 1 degree of freedom, 3.84. I need to reject my null hypothesis. The question is, what's happening? There's an outside force acting upon it because we're rejecting our null hypothesis. What is that outside force? Well, in the given situation, it's likely the fact that people like to buy plants that eat large flies opposed to plants that just eat small flies. All right. If you switch over to question 2, we're going to take a look at some newts. So there's a C question here that'll be on the next slide. So let's figure out this part first. Certain population of newts being poisonous, which is dominant, over non-poisonous, which is recessive. You count 200 newts and 8 are non-poisonous. What are the allele frequencies of the parent population? So again, what am I looking for? I'm looking for allele frequencies. So I'm looking for P and Q. All right. Q is going to be non-poisonous. P is going to be poisonous. But what am I given? I'm given individuals. So remember, this 200 is both P squared and 2PQ. This 8 is just Q squared. So again, I need to start with Q squared in order to figure out the rest of the information. So Q squared equals 8 over 200, which is 0.04. So the frequency of individuals in the population is 4% that are homozygous recessive for being non-poisonous. All right, so then in order to find allele frequencies, I have to convert to Q. So I take the square root of Q squared, and I get Q equals 0.2. What does that frequency mean? That frequency means that 0.2 of the alleles, 20% of the alleles in the population are going to be recessive or code for non-poisonous newts. All right, easy enough to find P. P is 0.8. Okay, moving on to 2B. 50 newts wash downstream. All right, and after a big storm, they colonize this new pond. What would the expected frequencies be for each of those genotypes? So we just figured out the allele frequency. We can figure out if 50 of the 200 newts, or 50 of this entire population of newts, were to wash downstream, we can simply use those same frequencies, or determine the frequencies, and then place them in relation to this population of 50. So what are we trying to find? We're trying to find how many homozygous dominant newts there should be in that 50, how many heterozygous newts there should be in the 50, and how many homozygous recessive newts there should be in the 50. Okay, so here you're using the frequency not for the allele, you're using the frequency for the individual. So for Q squared, that's easy, we already have that, that's 0.04. But we have to figure out what the frequency of the heterozygous and the homozygous dominant individuals are. So here's where I use those allelic frequencies. So the heterozygous is going to be 2 times 0.8 times 0.2, and the P is going to be 0.8 squared. This should give me 0.64. This should get me 0.32, and I already have 0.04. So that's the first step to solving this problem. The next step is saying, okay, so those are the frequencies of individuals I would expect in a population. Now I have to establish what's the size of my population in order to figure out the numbers of individual newts that will be there. So I take 64, 32, and 4%, and I multiply them by 50. So 64% of the population of 50 should be homozygous dominant. 32% of the population of 50 should be heterozygous, and 4% of the population for 50 should be homozygous recessive. So when I plug that in, I should get 32, I should get 16, and I should get 2. And if I've done this all correctly, what should happen to these? These should all add up to 50. That's because I'm taking into account each one of the different individuals. What you want to be really careful about, and a mistake that's often made, is that people use 0.2 right here. 0.2 again is Q, not Q squared. You have to make sure that you understand what it is you are attempting to find. I am attempting to find the number of individual newts in this population of 50 that should be homozygous recessive. Okay. Moving on to the part C of this. So you're going to need the information from 2B in order to answer 2C here. So 2C says you go down there to this new population and you count them up. You figure out that you have a P squared of 21 individuals, a 2PQ of 23 individuals, and a Q squared of 6 individuals. All right, so essentially this would be big P, this is big P, this is little p, little p. And this is what you observed. So let's calculate everything out and let's write down everything I know at this point. So here's what I know. P squared, 2PQ, Q squared. I know my expected and I know my observed. My expected for P squared is 32 from the last page. My expected for 2PQ is 16, and my expected for Q squared is 2. So those are the number of individuals I expect to be in the population. So we're talking genotype here, not phenotype. Then I observed, what did I observe? I observed 21 homozygous dominant, I observed 23 heterozygous individuals, and I observed 6 homozygous recessive individuals. So the question is, does the difference between each of these numbers, the difference between 32 and 2, 16 and 23, 2 and 6, is that statistically significant? Is evolution happening in this particular situation? Essentially, are the allelic frequencies changing because of some outside force or some reason? All right, so if I plug this in, now I have 3 options, right? Option 1, option 2, option 3. So here my degrees of freedom are 2, and my critical value, going back to that sheet from the first page, is 5.99. So that's what I'm going to be comparing it to. So again, I like to write it above just to make sure that I'm not making silly mistakes. So let's do the chi-squared for all 3. So P squared, my observed is 21, minus my expected of 32, square that, over 32. Add that to observed 23, 16 expected, squared over 16. And finally, 6 minus 2, squared over expected of 2. This gives me 3.78. This gives me 3.06. This gives me 8 for a total of 14.84. So what does that mean? That means that I have to reject my null hypothesis and an outside force is acting upon it. So what that means is when those newt drifted downstream, it's not that evolution is acting upon it, it's that the random chance of newts who went downstream did not fulfill the Hardy-Weinberg equilibrium in the original population. So all you're saying is that the original population and this population do not share the same equilibrium or allele frequencies. You would have to watch multiple more generations to see, does this population go back to being more poisonous, or does it evolve in a different direction? Because right now, if you look, that number 6 is suggesting that 6 of those individuals are non-poisonous. Well, if poison is a large enough advantage, you would expect that number of 6 to fall back quite quickly because those non-poisonous newts would be eaten. However, if poison is not the most essential selective advantage, perhaps they still have their coloration that might suggest they're poisonous, then all of a sudden either that number would stay and this would be a new Hardy-Weinberg equilibrium, or that number would increase if it's essentially a neutral situation where non-poisonous newts are able to survive and thrive. You could expect that number to slightly go up. I hope this makes sense. I hope this was helpful. Adios.